Question 11. We have two stars, right, mass m and 2m, going in circular motion about their common center of mass. So now, right, this system is actually different from our usual orbiting motion, okay? Because, right, now both stars are in orbit and they are not orbiting about a certain particular massive object, because both of them are really massive already. But instead, right, they are orbiting about a point in empty space, which is their common center of mass. To figure out, right, how to get this right, let's start off with a easy idea. Okay, suppose I have two fish ball, small m is mass 2 small m and m. Okay, and I poke a satay stick of negligible mass into them. Okay, so this is connected now. So where must I pivot, right, this system of satay stick and fish ball on, such that this whole system stays balanced? So with some idea of the moment, right, we can quickly, right, deduce that we need to balance this, right, closer to 2m, such that, right, the moment due to 2m equals to the moment due to m. And since we know the ratio of the masses, we can figure out, right, what is the ratio of the distance from their CG to the pivot that we must set. So suppose, right, the entire distance between them is called r. Then, right, or let's just call it L, okay, so as not to confuse with the R in gravitation. Then, right, this distance will be 1:2 of the distance to that mass. So altogether will be 3 part. So this will be L upon 3. The other one will be 2L upon 3. Yeah. So the ratio of the distance, right, is the inverse of the ratio of the mass. With that, right, we can figure out what is the where is the center of mass, okay, of this two star system. So in a similar way, right, I say it's similar in terms of the logic of figuring out, but right, the idea is actually not that of moment, so you mustn't mention anything about moment here. So the center of mass, right, will be this point, such that this will be r upon 3, this will be 2r upon 3. So how will they orbit? So this guy, right, will be orbiting, right, in this circle. Oops, it's really ugly. Then the other guy, right, will be orbiting in this circle. Okay, center of mass must not move. Okay, so this guy, right, if he orbit in this direction, then the other guy, right, must orbit in this direction. Okay, so that they are always, right, opposite each other with respect to the center of mass, which is to stay fixed. Okay, so with that, right, let's work out the mathematics of this thing. So suppose, right, we consider 2m. Okay, we look at the point of view of 2m. So what's to happen? So Fg provides for Fc, right? So we have, right, G due to m attracting 2m, okay, over r square. This is equals to 2m. The radius, you see, when you talk about mr omega square, right, you're talking about the radius of the circular motion. So for 2m, right, what is the radius? It's r upon 3, okay, omega square. With this, right, you can cancel away the 2m on both sides. You'll see, right, that the omega square is equals to 3gm over r cube. Okay, yeah, we don't know what that is, so we just leave it hanging for the moment. So let's consider, right, point of view of m. So you can see, right, the equation works out to be exactly the same. So G2m times m over r square equals to m, and what do we have here? 2r upon 3, okay, omega, let's call this omega 2 and the other one omega 1, because right, we are not sure whether the omega are the same or not. Okay, so now once again you eliminate all the common terms, you cancel out, you'll see that omega 2 square is equals to 3 gm over r cube. Turns out, right, this is equals to omega 1 square. Okay, and this is the result that you need to know for this kind of binary star system moving about common center of mass, which is, right, they will have both the same angular velocity, okay, and also, right, same period. Okay, same radius, confirm no. Same speed, confirm no, because, right, you have to cover a different circumference in the same time, so you can't have the same speed. Yeah, D is of course rubbish. Okay, so answer is B.